So just a brief introduction on basically what was the aim of this challenge. I mean, some of you know about the ESoWC calibration system and the ESoWC products. So basically, what we have is a complex system calibration software that we use to statistically post-process NWP model outputs that, as we put there, sometimes require some adjustments. And how do we do this? Basically using calibration, which is just very simple process to establish relationship between the forecast, past forecast, and observation. This process can be done as can be very simple. We just compare the forecast and the observations, or we can use certain conditional verification tools to make it a bit more. Well, I don't want to say complex, but actually it is, because it's basically using other parameters from, for example, from the model to see whether they can give us more information on the relationship that exists between forecast and the observations. And here we just show how this relationship can change and can change. So why we use ESoWC2019? What I have described now it was very quick, but it's a very complex system. And with the calibration software that we used at the beginning, all that complexity was left to the user, to the researcher, creating all the code, the examination of the data, so create the database and everything. With the calibration, with the ESoWC2019, we removed all that complexity from the user, and we made a more user-friendly software, so that actually the user can enjoy almost the process of calibrating. Thank you very much. So basically, the purpose of ESoWC2019 is allow the users to perform conditional verification and calibration tasks, which are, as I said, is an interactive and in an iterative way, removing all that complexity. And by removing that complexity, we just allow basically to be the whole process more reproducible. And this is an important aspect for two main reasons. We use this software to produce operational products, and by having this reproducibility quite clear, we can facilitate, for example, the diagnosis of this of the post-processed products, but also we can enable other researchers to use our methodology and actually expand the usage of this software. With that, I pass the microphone to Tim, that will show you actually what we do with the calibration software at ESoWC.
Okay, thank you, Fatima. Yeah, so we've kind of done the manual process so far, and based on that manual process of calibration, we have created products, real-time products at ESoWC. So we kind of, this is just to show you how kind of beneficial and the advantages of actually doing that. So here, this is kind of back to real weather. At the top, we have the top four panels these are cumulative distribution functions. So for people that don't know that is like the probability to not exceed on the y-axis, and here we're looking at rainfall. We've done calibration for rainfall so far, 12-hour rainfall on the x-axis. So the point about this is to show you that the relationship between the raw model output, which we're post-processing, and the post-process output, which is the point rainfall in this case, it varies quite a bit. So here, if you compare on the top four panels, the red line with the blue line, what you can see is there are different relationships between those, and that arises because we are using this conditional verification concept. It's saying that the relationship between the forecast and the observations varies according to mainly to the weather situation. So the top left panel, the blue and the red lines are similar. The next one along, where it says 170 millimetres, you've got a long tail, so that's saying we could get a huge amount of extra rain compared to what the model's saying. And then the two right examples are variations on the theme. The one with 35 millimetres on shows you that the post-processing is actually removing some of the rain because the model is biased in that situation. And then at the bottom, just to show you a kind of real-time example, this is from the flash floods in southeast Spain, September 2019. On the bottom left panel, you've got the 12-hour rainfall forecast from the raw ensemble. That's the wettest that the model came up with. On the bottom right panel, you've got the post-process point rainfall, and then in the middle, you've got the raw observations. So these are kind of worst-case scenarios, and the point here is that the post-process, with having used the calibration, etc., is much better able to represent the huge totals that led to lots of flash floods in southeast Spain. You see the blue dots near La Manga there. There's a 300 odd millimetres here in about 12 hours. So this is basically showing that this is a much more useful product when we post-process than the raw model output. And so we've done that already for ESoWC, but we want to do it for more model cycles. We want other people with their own models to do it. We want to do this post-processing for other variables. So the sky's the limit, which is why we want this GUI, which Anirudha is now going to explain to us.
So I'll present you the which is really an iteration over software that I already worked on in the last year. But to give you an overview of what this software is about, it mainly has these three components. First is calibration. We have a statistical post-processing component, which is suggesting the meteorological forecast based on calibration that you already performed. And the third part, which we also talked about in the introduction, conditional verification. So throughout the presentation, I will present you how the software is utilized for each of these three types. But before I do that, I'll go through some of the pain points that we had in the previous version of the software. It's funny to say because I wrote it. And let's just say that it was not that good. So the data loader for ESoWC was very slow and often unreliable. And some of the mathematical operations that we were trying to do in the software native back then. Basic, it's sometimes slow. Computation of predictors took several days sometimes to finish, even for 1 month of data. That works, but it's not practical. It was written in Python 2, which was some of the packages we were using. One example is pandas, and we really needed some of the features Python 3 release. And this was also a blocker for using MedView Python bindings, which is Python. It's a framework that has Python bindings. It couldn't handle large amounts of data, and the rendering of the data during the presentation, it was really choppy, unusable. So what did we do in the new version? Did a complete rewrite of the software. This time we used the interface with MedView directly. That gave us a lot of performance benefits. We're also able to port the entire software to Python 3. In the process, replace PC ports for loading data like grid files, and instead use the MedView Python framework. We were able to use efficient low-level data structures that made handling of large amounts of data quite efficient. And during computations, the streaming of logs to the GUI, there is a GUI represents. But this was, we were able to make this non-blocking, so even if the GUI crashes or for a while, the computation. Sometimes useful when you're computing for 1 year of data or 2 years of data. And the decision tree, I managed to make it to evaluate the decisions. So it's actually a technical term, but essentially only evaluating the decisions and deferring it to the point where they actually need the decision computer made. Yeah, so this is the first screen that you see when you open the software. Have the description, some links, and you have two things. You have two options in front of you. The first one is generate a new point data table, and the second one is create and test a decision tree. I'll first go through the first button through slides, and I'll do a live demo for the second one, which is so the first tab, when you click on the generate point data table, you can select observations. You can configure parameters related to your model data, like specify data format, things about computation parameters related to the model runs, calibration period, and so on. Also, you can specify a predictor, whether it's an accumulated one, and some parameters related to that based on what you choose. And we also ask the user to specify the variables that will be used for compute the predictors, the calibration process. So this is the screen for computing the predictors. This is more like a framework because we want the user to have flexibility in what kind of predictor she wants to use for the calibration process. In this small example, I'm using simulated total precipitation and vector precipitation. And I'm using these two to compute a third predictor, which is convective precipitation ratio. It's just ratio. First two predictors. I'm also, I have something called a scaling factor. If the units of your predictors are not according to what you like them to be, then you can you also have a multiplication factor, scale the values accordingly. Also have hints about the unit present in the original data, so it's just a hint. Scale the values. And finally, you can select the predictor you want used, because some of them are just present to be used as inputs to other predictors. For example, the convective precipitation, which is finally not used in the calibration process. In the next tab, we have we launched the computations and just a window where you will see the live tail of the logs. And it's also available from outside the software, so you just do a tail F, the path to the log file, and you see the same thing. So this is the point where I'm going to do a tightrope walk. this is the same page that we saw earlier in the slides. And now I'm going to click on the second button, which is Premium Plus Decision Tree. I'll use a point data table that was previously generated during your calibration process. And just to show that software is indeed able to handle large amounts of data, I just loaded 1 year amount of data where the calibration period was 1 year, which is a lot, and it just took a few seconds to. I can change the pins that will be used for the mapping function, but accept them as default. They are editable. And move to the text string. So this is really the core of the software and what makes the software so great. This page lets you construct or play with decision tree and taking as input the file that I just uploaded. As with any decision tree, you have levels. So these levels are the predictors read from the point data table. I can change the levels. I can drag and drop the segments and pick something that suits me. For example, let's say this is the level that I'm interested in having. Having levels is rearranging the levels is actually just changing the order of importance of the predictors in the decision. And then I click on generate the effect. I scroll down and I see a small single node decision tree with 0, 0, 0, 0, 0. It's called root. This is the root of the decision tree. And if I click on this, a mapping function that corresponds to one data table. It takes a few seconds because it's a lot of data, but this is the mapping function. A mapping function is just, it shows the relationship between the forecast and the observation for the data points. And the white bar is case where focus and the observation are more or less the same. The green is for overestimate and the rest for underestimate. I can save this image and maybe for future reference I can go back to the original view. Now we'll try to construct a meaningful decision tree on this point. And the way to do that is switch to a mode called edit mode. I can do that by going to this, toggling this radio button. And now I'm in edit mode. If I click on these mode again, I see something else. So this we ask the user to input a split value, which will be introduced at any given level based on what I choose in the drop-down. Let's say I want a state of 0.5. I click on split, and you see the vision tree is re-renders itself. I see the split. If I switch back to the normal mode, I click on any one underneath, I should see the change, and it will be according to the specific decision that I clicked on. Now, this is the case when you already know the split value that you want to introduce. Or if you don't know anything, you just have no idea what the value should be. So you can go back to the edit mode and ask the software to suggest you breakpoints. And the way the software suggests you breakpoints is by running a statistical test called Kolmogorov scale-off test. And it can be done at any level, just like in the previous case. Let's say you want to run this test for the base speed predictor. I click on generate, take a few. Right. So now I have a bunch of suggestions. At this point, I can save all the mapping functions corresponding to these suggested breakpoints in some temporary zip. I'll go through the images and decide to just keep the ones, keep the breakpoints that are interesting. By interesting, I mean the mapping functions should be significantly different. That's where they are interesting. And I could discard the rest. So in this demo, I'm just going to do some random complications, remove some breakpoints, and or even modify the values, and then introduce the split. So this is my new decision tree. And as before, if I go back to the normal mode and one of the leaf nodes, random one, then I should see corresponding mapping functions. So this is the statistical post-processing. Now this decision tree is really it's a visual representation, something that's displayed right here. So this is a tabular representation of it. We can save this file for the reference. So for example, if you want to use the same decision tree for some other foreign data table, then you can, in future, upload the CSV file and just have the decision tree constructed right away. So you won't have to go through each step constructing the tree. There's also a useful button to save all the data types as PNG files if you want to see all the mapping functions for a given decision tree. And yeah, that's it. The third section of my presentation, as I said, was beginning, was the conditional verification process. And in this software, we allow you to generate three kinds of conditional verification. Let's see the first one. It's observation frequency, and you can use the same decision tree to click on one of the nodes, and it will generate the map. Alright, so it's basically for every latitude and longitude. It's plotting the how frequently plotting the observation frequency, which we can save and then go back to the previous screen and plot other kinds of conditional verification maps. This time, let's take some other kind of node. Let's say this one. So this conditional verification map is about the mean value for the forecast error ratio. Depends whether it's a forecast error. And the third kind of conditional verification map is the standard deviation. Alright, and also save. One interesting thing about this decision tree is that have these colored rings, and this is to give the user a visual hint that they are different predictors. It can so happen that there are two different predictors at the same level. So it can get confusing if the user is not paying attention. Denote the text. Try to use unique colors to denote predictors in the tree. Yeah, so this is a useful feature if you introduce several splits and now you don't want them. For example, I think, let's say these two nodes, 10400 and 10, they are useless according to me. Then I can go to this table and find them by the data type code and use this one button to merge them together. I want to do this like this and see the whether tree filter itself. Yeah, so we now have one less weather type. And I can keep on doing this for as long as I want and eventually end up with the root node. We only show these merge buttons for weather types that can be merged. We figure that out looking at the breakpoints. So for the ones where the merge would result in an invalid state of the decision tree, just don't show the option, don't give the option to merge. Okay, that's it with the demo. Go back to my slides. Brief note about the software architecture. So the entire software suite is two Docker services are running inside containers. We have three main containers. The first one is core of the software that's running a web app written in Python. It's using a framework called Just. And we use some scientific computing packages available in Python, like matplotlib for plots, xarrays, and numpy for very efficient arrays, pandas for data frames, and scipy for figure tests that I showed. We are actually also running the medview process right in this container, so the user doesn't have to do anything. We have a bridge, which is the medview Python binding for associated medview process that the Python code can configure. The web app server is exposing a REST API. This is consumed by other container, which is running the GUI just off. The GUI is built using something called Electron. It's a desktop application framework that I have built by using React as the Vue framework and Redux for state management. And Electron also interfaces with the native operating system. So things like opening a dialog or saving a file, it offers us a lot of user-friendly tools to do that. And finally, we have a small container that has the logger agent. This is just feeding the logs to the Electron server. And this is done through a WebSocket connection, which is a full duplex communication channel. And this makes sure that core and the not blocking each other when producing logs. So software can produce logs at its own speed, and then we can display in a self-paced manner. So, here are some of the things I learned as part of the ESoWC. So I got a lot of insights into calibration and analysis of weather forecasts, but I got these insights in the real world. I was working with real life data and something that would be used for hopefully. I also learned that Python is highly expressive, mature, and performant language, especially for scientific computing. Just some words of advice: don't use Python 2. You're starting a new project. Also, don't use MATLAB, if possible, okay, because it's 2019 and using Python 3. Building fluid user interfaces is really, really hard, but Electron is your best bet. If you're writing a desktop application, use Electron. It's cross-platform. And you can use JavaScript. So. This is a really nice quote I've read somewhere in a book. What the mind can conceive can achieve. But when it comes to user interfaces, only if you use React. So use React for building your user interfaces. And lastly, I also learned how to think from first principles. We're aware of this concept is popular. Where you break down the problems into sub-problems so that they satisfy some ground principles, and then you work your way up, basically divide and conquer. What this can result in is you may need to trash 75% of it, is what happened to us. But in the long run, it really helped us get where we have to be. So don't be afraid of doing that. Of course, no project is complete without its collaborators. And I'd like to present you the collaborators in the next slide. So they are our mentors, Fatima, Tim, and Rio. And we had a lot of fun doing weekly calls on this. It was fun, especially with you. And yeah, that's it. Thank you for. Questions.
Any questions?
Thank you. Very interesting. You mentioned data. How much data amount you use now for the music? What do you think would kill it?
So in the live demo, we used a point data table that was operated on 1 year of 1 year calibration period. And the size of the point data table was 300 megabytes of plain text, which is a lot. So you cannot even open that in a regular text file sometimes, text editor sometimes. But when we saw that Python is not that bad handling such levels of data, but of course for generating the more computationally expensive plots, the maths that I showed can take several seconds. But with 1 year data, I think that's not that bad. With something much smaller, like 1 month or 2 months, it's instantaneous. You wouldn't even see the math. And I've tried to, in the user interface, I've tried to make things because humans have, for example, you click on a button and we asynchronously start generating the new decision tree. So by the time you scroll down to see the actual tree, it's already rendered. So these are some of the tricks that we use to improve the experience. Generally speaking, software can today work on like
just to add to that briefly, the principle with the calibration software is that what you need is 1 year of global data. Generally speaking, you shouldn't need any more of that. So this is perfectly adequate for your tasking.